So, in continuance of the previous lecture, I was discussing about the characteristic of a system. Say, characteristic of a system, we need to have the idea of the order of the system and type of the system. For example, we are taking one system like s square plus 8s plus 25. See, what I was discussing about, this is the highest power of s in the denominator. This is your denominator part, and highest power of s, that is highest power of s is equal to 2. So this is a second order system. Whatever may be the value or power of s in the numerator. Say this is 4s plus 1. This may be only 1. This may be 4s square plus 1. This may be 4s cube plus 1, whatever. So you need to concentrate on the power of the s, highest power of the s in the denominator. Now this is known as the order. And you see, already I have discussed a certain part, that is, say for example, in this case there is no pole at s is equal to 0. Is there any pole? No. So if the transfer function is like, say, gs is equal to 4s plus 1 into s square plus 8s plus 25. So you see, there are 3 poles. If you multiply this term, what you will get in the denominator, highest power will be 3. So definitely this will be a third order system automatically. And if this is a third order system, also or simultaneously, what you get the pole at s is equal to 0. So a single pole at s is equal to 0. That means this is a type 1 system. So these are the parameters which is very much actually useful. So if the transfer function is, say, gs is equal to 4s plus 1 by s square into s square plus 4s plus 10. So what happens here in this case, there also, if you multiply the denominator part, you get s to the power 4 in the denominator. That means highest power is equal to 4. So this is a fourth order system. And order you can identify, so simultaneously you can get, say, at s is equal to 0, there are 2 poles. How many numbers of poles in the denominator? At s is equal to 0, 2. So this means this is a type 2 system. So that is how you can recognize whether a system is a type 0 system, what is the power, what is the order of the system. Similarly, what is the type 1 system and type 2 system and type 3. That means number of poles at s is equal to 0 indicates the order of the system, and this order of the system along with the power of the system, sorry, s is equal to number of poles at s is equal to 0 indicates the type of the system. And once you know the type of the system and order of the system, that means that gives you some idea about the characteristic of the system. Now as we have to get the roots, that means previous lecture we were discussing about the positions of the roots, and the positions of the roots plays very important role for the performance analysis of any order, any type system. Now I will just briefly focus on that part. We already know the characteristic equation. So characteristic equation of a closed loop system is equal to your denominator, which is a function of s. So in this case, if you consider this transfer function, this is a second order system, you see, and the denominator is s square plus 8s plus 25. So if you make s square plus 8s plus 25 is equal to 0, this will be your characteristic equation. Now there are two roots. If you solve it by using Sridhar Acharya, what will you get? S is equal to minus b plus minus root over b square means 64 minus 4ac, 4 into 25 into 1 divided by 2. So this will give you minus 8 plus minus root over 64 minus 100 by 2. So this is minus plus minus 36 minus by 2. So this is under root minus 36. So definitely we will get complex value of it, that is minus 8 plus minus j 6 by 2, that is minus 4 plus minus j 3. So what we get? You get the two values of s. See, one is say s1, that you can write minus 4 plus j j3, and second root is equal to minus 4 minus j3. These are the roots. These are known as roots or the poles, right? Once you get the poles, that means these poles, this minus 4 plus j3 minus 4 minus j3, what does it mean? Actually that means nothing but, as this is the value, these are the values of s, so these are the pole locations on the s plane. If you know this value, this is your real value, this is your imaginary value. As we are discussing about the s plane, so s plane means s is equal to sigma plus minus j omega. This is the equation of the s plane, where s is the Laplace domain equation function, and this is your real part, plus or minus j omega. See, this is your axis, this is your real axis, this may be sigma, this is your imaginary axis, that means this is your j omega axis. So if this is plus j omega, this is minus j omega. Also there may be like this. For simplicity, what will you get? S is equal to sigma plus j omega. That equation is considered, and the values of real value and imaginary value will give you the total s plane equation. Now, as in the case of normal xy coordinate system, what will get? See, this is s1 minus 4 plus of j3 minus 4 will be, if you have to move minus 1 minus 2 minus 3 minus 4 like this, and then you have to move by 3 values in the j axis. So 1 2 3. So this is the location, that means this is your location for minus 4 plus j3. Similarly, you get minus 4 minus j3. So minus 1 minus 2 minus 3 minus 4, you go in this direction along the real axis by an amount of 4, then you have to move 1 2 3. So this will be your minus 4 minus j3. That means once you get the roots or poles of the system, then you can have the idea where these poles are located. Say for example, in any case, if the value of, if s is equal to plus 4 plus j3, then where will it be located? This is plus 4, that means 1 2 3 4 along this axis, then 1 2 3. So this is the location of the pole. So you get the locations of the poles like this in the s plane. Similarly, if you solve the numerator, what we will get? That is known as the 0. Once you solve the denominator, that is known as poles or roots. Once you solve a numerator, you get these are the zeros. So how can you get the zeros? That means in this problem, if you make 4s plus 1 is equal to 0, the value of s will be equal to minus 1 by 4. That is, it is having only the real values, and real values is minus 1 by 4. Minus 1 by 4 means minus 0.25. So minus 25 is somewhere located here. So this is the position of the 0, right? So this is how on the s plane you have to place all the poles and zeros of a given system from the closed loop transfer function, right? So if you place the roots, that means poles and zeros on this s plane, then there will be probability of getting the stability criteria, and the stability criteria will be discussed in later on. Now our aim is to get the roots, that means in order to get the characteristics of any system, you have to find out the system to be first order, second order, third order, fourth order, whatever, type 0, type 1, type 2, type 4, whatever, and finally you have to find out the roots and where the roots are located on this s plane. That is all about the system description, right? Once you get the system description, next part the performance specification. I will discuss about the defined performance specifications during the analysis of time domain performance specifications of any control system. So what are the defined types of performance specifications and how it could be obtained, right? So in order to have this, I have to just find out, or I have to write this transfer function as a whole. This is your gs by 1 plus gshs and cs. You know what is this gs by 1 plus gshs? You know from the first chapter, that is, this is your closed loop transfer function. As we are discussing about the closed loop system transfer function and response of it, so performance specification is solely depends upon the closed loop transfer function. So what happens, see, this is your transfer function in short, and this is your rs, that is your input, and this is your cs, that is your output. So what will get actually, say if you simply replace it by only gs, right, you write it as gs. So cs will be equal to rs into gs. That means this is your system and this is your input. Now you know the characteristics of the system already and the different types of standard inputs. What are the different types of standard input? Again I say the impulse, step, ramp and parabolic. If you apply any one kind of this input to any system, you can get the output and according to this. And what is the desired specification of any control system? For any control system, the desired specification is that the output must follow the input, right? For example, if you apply a step signal, that means how the step signal looks like, we know this is your unit step signal, this is your amplitude, and this is your time. So for every value starting from 0 to infinity, you will be having 1. So if this kind of input is applied to any system, so according to your desired specification, output should be like this. This should be your output. This is your output. This is amplitude and this is time. So t is equal to 0. This should be your output, right? Now input and output must be same in order to get a system to be controlled, right? So output must follow the input, but in practice this actually does not resembles this. So there is a difference between these two, but ultimately aim is to get that output. That means there may be different way how this output may follow the input, right? So that part I am going to discuss, how this output is going to follow the input for different types, different order system for different types of input. Say input may be not like this, input may be this. If this is your input, then also say this is your input, output corresponding to this should be like this, right? This should be your output, but actual this output is not following in the similar fashion. There is certain difference, and how this difference is obtained, that we will mathematically show. So to know the how the output actually following the input, we have to know the the different transient response and steady state response parameters. Now the what is this transient response and steady state response? Say for example, I am taking the graphical representation only, mathematical part I will show you later. So this is your time, this is your amplitude, and this is your one, that is your step signal. This is your step signal. And a second order system, closed loop transfer function, this is your closed loop transfer function of a second order system, say 25 by s square plus 8s plus 25. this is considered. Now, if any type of step input is applied to the system, always the output curve, this is your output response curve, you see, this is your time, this is your output, so this is your amplitude, and see how it is following. It is following like this, you can see it. So like this. So what you will get, you get the different sections. You see, this is your input, so output is only having the value input after certain interval of time. See, initially when you start, what happens, this is following like this. That means initially when you start at t is equal to 0, you switch on the system. What happens, that means you have applied the step input. So this step unit goes through this system, and depending upon the system and input, some output is generated. How generated? That means there is a oscillatory part. So there is a oscillation about the desired point. This is your desired point, right? This is your desired value, and this output is trying to get the output value. But initially there is certain value of the output signal, see, above the desired value. After this time, there is a certain value of the output signal, because this is your output curve, right, and this is your input curve. So this output curve is varying like this, and after certain time interval, say this is ts, you get certain value of output which is very close to input value, or there may be straight line where you can see there is no difference between this output and input, right? So there is a two sections in any type of response characteristics when you study. This section is known as your transient. Transient means there is oscillations about the desired position. This is your desired position, and about this desired position there is certain oscillation. That means oscillation persists, right? And after certain time, say ts, maybe 5 second, 10 second, 2 second, 0.1 second, whatever maybe, after this you get the value of the output is very close to input. That means or actually equals to input. So this part is taken as steady state. So steady state, theoretically the steady state reaches at t is equal to infinity, and that I will discuss in detail. But the thing is that in this part I am just want to get you understood about the transient part and steady state. So transient part is that from certain time, starting to certain time, you get the oscillations of the output signal about the desired value, that is about the input signal, and this is known as the transient part. And then after certain interval of time, you get the output is almost very close to input. That means actually there is no maybe some error, but the oscillation dies out. Basically in case of transient, in short I can say oscillation exists, and in case of steady state, oscillation dies out. That is the basic difference between the two regions, transient part and steady state part. And once the transient part and steady state part is defined, that means there is certain parameter which defines these states. So the transient part's parameters, next part, the parameters. First transient section, next steady state section, right? So what is the transient parameters? Transient parameters are normally known as rise time, peak time, peak overshoot, and your settling time. and steady state parameter is steady state error. So you see, this is the output response of any second order system corresponding to step signal. And in most of the cases in the industry, normally the standard input signal which is used is step, right? Why are not impulse, not ramp, not parabolic signals are normally used? So these are the kind of inputs available as you have discussed earlier, but the normal cases or maximum cases the standard test signal is taken as step, because you see the characteristic of the step. This is your step signal, say this is your step signal. That means its amplitude is constant throughout. So if any system is to follow it, that means there is a constant value after certain interval time. And in case of ramp, what happens, you have to follow this type of curve. In case of parabolic, you have to follow this kind of curve. So the getting the error signal, so we will discuss about the error signal in case of ramp signal and parabolic signal, as is very difficult. So in this case, step signal is used as the input signal for any kind of signal testing. So we get the defined parameters corresponding to transient and steady state. Now how can you understand these parameters, and what is the parameters you can get from the output response? That I will discuss in detail when the mathematical formulation I will show. Now you know these parameters only, and now I am going to discuss in detail about the different types of input, different order of the system, how the output curve is actually look like. We will identify the defined parameters from output response curve, right? So let me redraw the output response curve. This is your time axis, this is your amplitude axis. Now we are applying, this is your unit step signal. So definitely this curve is input. Now I am just giving example of a say a second order system. So for second order system, the response characteristic curve is like this. See, what are the parts? First of all, you have to identify starting from t is equal to 0, that is initial time, up to certain time where the transient signal exists. See, we have to consider that part. That means here, see, up to this part, we will consider this. Up to this part is your transient part. Why this? And see, there is also certain very small tiny oscillations, and that much oscillation is also or can be considered as the steady state. When? So there is certain conditions that I'm discussing in this section. Say, let me see, this is your oscillation part exists, and there your steady state where the oscillation is not there, almost not there, or very small, which can be taken to be steady state. Now what are the defined parameters? You see, this is your oscillatory behavior. So first time, this time, the time, see this time, this is the time axis. So from 0 to this time, at this time tr, this is known as tr, where the output, this is your output curve, reaches the input desired value for the first time. See, there are different times. Here also some time is there, you can get. Here also some time, after certain time. Here also after certain time you get the desired value 1. But this is the first time, right? So first time when this output reaches the input, that is known your rise time. So rise time is denoted by tr, that is from this point to this point, and in the time axis you get the value, right? This is your TR. Now what happens about this? See this part. What is this area? You see, this area is just above the desired value, right? Above this. So this part is known as the overshoot. What is this? This is overshoot. Overshoot means the output curve actually exceeds the desired value, above the desired value. So this is the maximum value, peak value of the oscillation. So this is one time only. This is known as peak time. Peak time is equal to TP. That is a single value of time when this output curve reaches its maximum value. This is your peak time. And what is this? You see, up to this we have considered the transient response. That means this is the time when you are entering into the steady state value. So when you are reaching the steady state value, that is known as settling time, that is TS, and we are considering these as settling time. See, though there is a very small oscillation about the time axis, real value. So how much oscillation is actually tolerable? So that is known as tolerance. See, oscillation band. This is our oscillation band. You can see it. This is our oscillation band, and this band is known as tolerance band. How much tolerance is accepted, right? So there are two types of band. One is 2% band, one is 5% band, right? So this is your settling time. Once it reaches the steady state value, so you have to consider the band, right? That means the band of oscillations. How the band of oscillation is defined? See, I'll show you. This is your input desired value, and oscillation is like this. And if you see the band is like this. So what are the values of the band? We see there are two types of band. So if this is input, that means its value is 1, and 2% of it, that means 2%, 1.02, 1 plus minus 2%, right? And this indicates 1 plus minus 5%. That means 0.98 to 1.02, or maximum 0.95 to 1.05. These are the values of the output signal about the real axis. This is your desired value. So this value may be 1.02 or 1.05, and this value may be 0.98, 1.02. So if the oscillation is very small in such a way that the maximum value of the oscillation and minimum value of the oscillation lies between these two values, 1.02 and 0.98, or 1.05 in or 1.02, then also this is considered to be, this is 1.05. So if this exists, then also you take it at settling time, and this is your steady state point, right? So what is the parameter you will I have already obtained for second order system step response. This is for second order system. This is for second order system. Now rise time already you have obtained, peak time obtained, settling time obtained, and one is that peak overshoot, right? And another thing is that there is a undershoot. What is the undershoot? Undershoot means the area which is just under the desired value. This is your desired value, and the curve is under this. So this is your undershoot. So above the desired value, this is overshoot. This is also overshoot. Similarly, this is also undershoot. Similarly, this is also overshoot, and this is also undershoot. So there are certain undershoot and overshoot. So in order to get the percentage, that means peak overshoot, we have to get the value. Peak overshoot is denoted by T. Peak overshoot. Peak overshoot is equal to MP. Peak overshoot means the difference between, we have to get the difference between this point and this point, right? So if this is actually MP. This is your, and this is normally denoted in percentage peak overshoot. That means normally this is denoted by percentage MP, right? So these are the four transient response parameters, and once you reach to the steady state value, so there is a chance of getting error, that is known as the steady state error, right? Now I am just discussing about the steady state error. In order to get the steady state error, we have to get the error first. Let me just uh, get the, this is your say open loop transfer function, this is your output, this is your HS, and this is this. So what is this actually? When you will get the output minus input, or input minus output, that is, this is your error block, as you know. So one input is RS, another input is actually the feedback. If HS is equal to 1, say for unity feedback system, what happens? This signal is nothing but CS. So what is the output of this block? This is known as error, right? So this is error ES, as you know from the block diagram in the previous classes. So ES is equal to your RS minus CS, no problem. So this is the error, right? And actually we are talking about the steady state error, right? Very important parameter, steady state error, normally denoted by ESS. What is this? This is very important parameter. Steady state error means when the system reaches the steady state, that means after the settling time is achieved, right, where there is a error, right? If the curve is like this, I will redraw the curve like this. Say this is your input and curve is like, so this is your TS, T is equal to 0, right? See, this is your settling time, it reaches the settling band or settle down. What happens? This is your input and you see this is your output. So what you get? There is a difference between the input and output, and the difference between the input and output is denoted by error, right? And this error is occurring when the system reaches the steady state value, so that is known as the steady state error. So this is your ESS. That means theoretically at t tends to infinity, that means normally ES is ET, right? Because already we have discussed that all the terms are in time domain, so this is your ET. So when this amplitude versus time graph we are getting, so we are getting this as ET, right? This is your function of time. So ET is your steady state error when limit t tends to infinity. So at theoretical value t tends to infinity means at a larger value of time. So at a larger value of time t, if you get the difference between the output and input, so that will give you the steady state error, right? And normally this et is the error in time domain. Now if you get the Laplace transform of it, then et Laplace transform, if you get the Laplace transform of et, so you will get E of s, right? So Laplace transform of et, you will get E of s. And you know the final value theorem. What is the final value theorem of the Laplace transform? Steady state error, that is your ESS error, ESS. That is actually in theoretical case we see limit t tends to infinity et, right? So this expression, if you apply the final value theorem, you see dt is equal to limit s tends to 0, s into es, right? So by using this formula you can get the value of steady state error. So now till this time we have discussed about the different parameters of a curve, output response curve, that means rise time, peak time, overshoot, and settling, and the settling time, settling band, and steady state error. So these are the parameters of transient response, that is transient section, as well as the steady state section. And the next part of this class, I will discuss the step response, impulse response of a first order system, and step response of the second order system. That is the mathematical formulation, how this kind of curve is coming, and from that curve how can you find out these parameters.